Hey guys, let's finish up our journey on Japan MO Finals. Here is the problem 5. We define a set S as a beautiful set if for any distinct elements xyz in S, there exists at least one of them dividing the sum x plus y plus z. And the problem is to prove that there exists an integer big N such that for any beautiful set S, there exists an integer ns such that all elements in S are multiples of this element ns except at most n of them. And moreover, we want to determine the smallest n. So from a first glimpse, the problem is given in a slightly strange manner. So I find the best way to understand it is to construct by yourself a beautiful set. Then let me start showing you my construction. In order to maximize the number big N, we want to put as many whole prime numbers as we can. As usual, let's start with small numbers. It's easy to check that we can put 1, 2, 3, 5, 7 into S. Then now we add another element, let's call it x, and try to figure out what conditions we need on x. Indeed, it's a good idea to set x as an odd number, because in this case, for any triple 2, anything, and x, we have that 2 divides their sum, because every other number is an odd number. Now it remains to check the other triples. So we have another 3 triples, 3, 5x, 5, 7x, and 7, 3x. And for each of the triple, we need to find an element that divides the sum of the other two. Then let's start with a random relation. Say that 5 divides 3 plus x. This implies that 5 does not divide 7 plus x. So now if we consider the triple 5, 7 and x, necessarily we need to have 7 divides 5 plus x. And similarly, this means that 7 does not divide 3 plus x. And finally, this means that 3 divides 7 plus x if we consider the triple 7, 3 and x. Now if we put anything together, we have that x is congruent to 1 modulus 2 and x is congruent to 2 modulus 3, 5 and 7. And by Chinese reminder theorem, there exists such x, and the smallest one is 107. So now we have 107 into the set. Now let's try to add another number. I will call it x again. So the very first idea is to say, why don't we use the exact same relation as before? Let's see what happened in this case. So if this is the case, then 107 is congruent to x modulus all these numbers 2, 3, 5 and 7. Now since we add a new number, we have more triples to be considered. Let's take the triple 3, 107 and x. So since 107 is congruent to x modulus 3, then 107 plus x is not divided by 3. So if x is larger than 107, then necessarily we need to have 107 divides 3 plus x. If we apply the same arguments on the other triples 5, 107 and x, then we are in trouble, because with the same argument we need 107 divides 5 plus x. Well, this is impossible because 3 is not congruent to 5 modulus 107, which is a contradiction. So here I use the assumption that x is larger than 107, but it is really the same thing if x is smaller than 107. in which case we have x divides 3 plus 107 and x divides 5 plus 107, and you will see that, well, this cannot be the case, except x equals to 2. Then the lesson we learn here is that we cannot use the old relations, and this is the reason why we cannot have too many elements in the beautiful set. So let's start develop new relations. Indeed, there is a unique way to do it, because previously we assume 5 divides 3 plus x, so here we need to interchange them, which means 3 divides 5 plus x. And this implies 3 does not divide 7 plus x. But there is a good news. This implies that 3 divides 107 plus x, because 107 is congruent to 5 modulus 3. So now if we consider 7, 3, and x, we need 7 to divide 3 plus x. So again, similarly, 7 does not divide 5 plus x. Unfortunately, 107 is not congruent to 5 modulus 7, so 7 does not divide 100x plus x neither. And this implies that we need to have 5 divide 7 plus x and 107 divide 7 plus x as well. Then we have another good news, because 107 is congruent to 7 modulus 5, so 5 divides 107 plus x. So now we have covered all the triples, because 3 divides 107 plus x, 5 divides 107 plus x, and we assume that 107 divides 7 plus x. So let's summarize all this relationship. We need to have x is congruent to 1 modulus 2, x is congruent to 1 modulus 3, x is congruent to 3 modulus 5, and x is congruent to 4 modulus 7, and finally x is congruent to minus 7 modulus 107. So again, by a Chinese reminder theorem, there exists such an x, and this will give us the other elements in the beautiful set. Indeed, the smallest x that satisfies all these conditions is 10,693. It is really hard to guess the number if you don't go through this analysis. So now we get a beautiful set with 7 elements, and each 2 of them are co-prime to each other. So this means that n equals to 6 for this set, because we can pick n as any of them, let's say 2, and this rule out one element. Then now it is not difficult to convince yourself that we cannot add more elements into it, because otherwise we will encounter the same relations, which cannot be the case by our previous analysis. So this suggests that n equals to 6 is the answer. We are going to prove that 6 is indeed the answer, which means for any beautiful set S, at most 6 elements are not a multiple of some number n S. In particular, if there are less than 6 odd numbers in the set, then we can simply take n as equals to 2. This do the job. Now let's assume that S contains at least 7 odd numbers. Then at least 6 of them are larger than 1, because we can always add 1 into the set. And let's call them A1, A2 until A6. They are all larger than 1. And moreover, we assume that A1 is the smallest odd number larger than 1. Then my claim is that A1 divides all the other odd numbers. So for any odd number in S different from 1, A1 divides it. Before moving on, let me prove some very useful lemmas. The first one is the following. Let's assume that we have three odd numbers, x smaller than y smaller than z. Then my claim is that either x divides y plus z or y divides x plus z. So by the assumption of a beautiful set, it is also possible that z divides x plus y, but this cannot be the case if x, y, z are odd. So the reason is that x plus y is smaller than 2z, and moreover x plus y is even. This means that x plus y is different from z. So this implies that z does not divide x plus y. So this finishes the proof. The second lemma is closely related to the first one. We assume that now we have four odd numbers, a smaller than x, smaller than y, smaller than z. And the claim is that a must divide one of the sum x plus y or y plus z or z plus x. Let's prove it by contraposition. So assume that a does not divide any of these sums. Then by lemma 1, if we consider the triple x, a, x, and y, we necessarily have x divides a plus y. So similarly, we have x divides a plus z and y divides a plus z. Now let's consider the triple x, y, and z. So we must have x divides y plus z or y divides x plus z. But none of it is possible, because if x divides y plus z, then x divides the sum of a plus y plus a plus z minus y plus z, so x divides 2a, which means that x divides a because x is odd, and this is not possible since x is larger than a. Now if y divides x plus z, again we run into trouble because this means that y divides x minus a, but again y is larger than x larger than a. So in both cases we run into contradiction. Then let me show you how I'm going to use this lemma. So in particular I will consider a as a1 and x, y, z as any elements a2, a3, a4, a5 or a6. So I will formulate this as a graph problem. In particular, we draw an edge between ai and aj if a1 divides the sum ai plus aj. So for example, if a1 divides the sum a2 plus a3, then I draw an edge between a2 and a3, and so on. Then lemma 2 is simply saying that for any three vertices, let's say a2, a3, a4, there at least one edge in it. So this holds for any three vertices among these 5 points. So my claim is that there exists at least one triangle or a 5 cycle in this graph. Then now the problem turns into a simple graph problem. So the way I'm going to prove it is to consider the degrees on these vertices. So let's take a look on this vertex A2 with the simple case that A2 has degree 1. So assume that A2 is connected to A3. Then now we see that A2, A4, A5 is not connected, but by the lemma A2, A4, A5 has one edge. So this means that A4 is connected to A5, and the same A5 is connected to A6 and also A4 and A6. So A4, A5, A6 form a triangle. And now let's consider another case that A2 has degree 3. So let's assume that A2 connected to A3, A4 and A5. So I want to remark that the order does not matter. And in this case, there is at least one edge between A3, A4, and A5. This forms a triangle with A2, so this case also works. Now it remains to consider the case that every vertex has a degree 2, so any one of it is connected to two other vertices. And it is easy to see that the only possibility is to have a 5 cycle. Believe me, this will work. I will leave the proof to you guys. Now we are in the shape to prove that A1 divides any odd elements in the beautiful set. So let's assume that there is a triangle. So in particular, this means that A1 divides AI plus AJ, A1 divides AJ plus AK, and A1 divides AI plus AK. So if I add the first one and the second one and minus the third one, this implies that A1 divides 2 times AK. So if I do it cyclically, this means that A1 divides 2AI, 2AJ, and 2AK. And since A1 is odd, this means that A1 divides AI, AJ, and AK. And next we take an arbitrary element X in the set S, which is odd, and we are going to prove that A1 divides X. So indeed, let's consider the triple A1, AI, and X, and assume that X does not divide it by A1, so A1 does not divide X. So in this case, A1 does not divide the sum AI plus X, otherwise A1 divides X. Also, AI does not divide A1 plus X, because A1 divides AI. So now, the only possibility is to have X divides A1 plus AI. But we are in trouble because we have other triples A1, AJ, and X, AI, AJ, and X. For the same argument, we can say that X divides A1 plus AJ, and X divides AI plus AJ. And this implies that X divides A1, but A1 is the smallest one, so this cannot be the case unless X equals to 1. So for any odd number larger than 1, A1 divides X. Then the 5 cycle case is really exactly the same. So we can prove that A1 divides each individual in this 5 cycle, and then we can say that for any X, A1 divides X. Well, as soon as X is an odd number. To summarize, we prove that if there are at least 7 odd numbers, then any odd number is a multiple of A1, except the number 1. And now we are going to add the even numbers into play. And my claim is that at most one even number is not a multiple of A1. Again, I'm going to prove it by contraposition. So let's assume that we have 2 even numbers. Let's call them B1, B2 to distinguish between the odd numbers. And A1 does not divide B1, and A1 does not divide B2. By the same reason as previously, if we consider the triple B1, A1, and AJ, then necessarily B1 divides A1 plus AJ. And similarly, B1 divides A1 plus AK, AK plus AJ. And this implies that B1 divides 2 times A1. Then by assumption that A1 does not divide B1, this implies that B1 is smaller than 2/3 of A1. And similarly, we have that B2 is smaller than 2/3 of A1 as well. And now we consider the triple A1, B1, and B2. But we are in trouble Because A1 is odd, so B1 does not divide A1 plus B2. So for the same reason, B2 does not divide A1 plus B1 as well. Sorry, this must be A1. And moreover, A1 does not divide B1 plus B2. The reason is that B1 plus B2 is even and is smaller than 2 times A1. This gives us the contradiction. So at most one even number is not a multiple of A1, which means that we can simply take an S equals to A1. So there are at most 2 numbers which is not a multiple of A1. One is possible the number 1 and the other one is an even number. And this finishes our proof that 6 is the answer. So the proof is a bit long, so hope you don't get lost in between. If you like it, don't forget to subscribe to my channel. I'm Red Peak. See you, bye bye.